We've got some exciting news here, guys. This is the 10th and final test of convergence. It's the root test. It's not so bad. It's a lot like the ratio test in that we're taking a limit of something, and if that limit is less than 1, then the series converges absolutely. If the limit is greater than 1 or infinite, then we can conclude that the series diverges. And then exactly the same as the ratio test, if the limit equals 1, then the test is inconclusive. So the only difference is that we're not taking the limit of the ratio of consecutive terms, we're taking the limit of the nth root of the nth term. So the nth root of the nth term is what we're looking at every single time. That isn't a very pretty thing to do unless we happen to see a lot of n's in the exponent, and then it becomes quite simple. That's why I say this isn't used all that often, because it's only for things where we see an n in the exponent. So anyway, let's take a look at this. We're going to go ahead and look at the limit as n approaches infinity of the absolute value of the nth root of the nth term. Oops, I put the absolute value in the wrong place. We want to make sure that the absolute value bar is inside the radical because we don't want to mess with any imaginary values. So we'll absolute value it, make sure it's positive, and then we'll take the nth root of it. Of course, that doesn't matter here because all of our terms are positive. So we'll take a look at the limit as n approaches infinity of the nth root of e raised to the 2n over n to the n. These are not pretty things until we take the nth root. And then when we do that, we get simply, taking the nth root is the same as raising to the 1 over n power. So we're dividing all of our exponents by n. So that e to the 2n becomes e to the 2. And that n to the n becomes n to the 1. And remember that this is a constant. Does not get bigger as n changes. So as n gets bigger and bigger and bigger, we get a smaller and smaller value. This is equal to 0. This limit is equal to 0, which is in fact less than 1. Therefore, the series converges absolutely by the root test. Don't say the RT because I might think you mean the ratio tests. All right. So this one looks kind of easy to deal with the root test because we love to see that n in the exponent. Think root test when n is in the exponent. So we're going to take the limit as n approaches infinity of the nth root of the absolute value of the nth term. Okay, so we basically end up with the n's cancel out, n over n is gone. The absolute value gets rid of that 3, and we have 3n over 2n plus 1. And that's a very simple limit that you learned how to deal with back in Algebra 2 when you were learning horizontal asymptotes. This is just 3 over 2. 3 over 2 is greater than 1. Therefore, the series diverges by the root test. QED. All right. See how easy it is? If we have an n in the exponent. All right. Uh-oh. Famous last words. Now we don't have an n in the exponent, but if we take a look at the limit as n approaches infinity of the nth root of n over 2 to the n, we don't have an n in the exponent in the numerator is what I meant. We'll take the limit as n approaches infinity of the nth root of n divided by, this is 2 raised to the n divided by n. So that's going to be just 2, right? Yeah. What does the nth root of n approach as n goes to infinity? This thing growing is going to pull our value to be bigger, but this n growing is going to pull our value to be smaller. I feel like this might be an indeterminate form. We could certainly spend some time trying to calculate this. Or we could say, you know what, maybe the root test is too hard and we can try something different. For example, limit comparison tests, right? We can use the limit comparison test because this looks an awful lot like geometric. And the limit comparison test will do very nicely on this one. Perhaps the ratio test would also do very nicely on this series. This one perhaps is not the best, but maybe we could try it anyway. I'm always up for a math challenge. I think we can do this. So let's do this as a separate problem. I'll change colors and we'll do, let's assume that the limit as n approaches infinity of the nth root of n, which is n raised to the 1 over n, converges to some value y. We'll take the natural log of both sides. That seems like a reasonable thing to do. So we'll take the natural log of y, and we'll take the natural log of n raised to the 1 over n. Well, the reason we would do that is because we could pull that 1 over n out front. So it's 1 over n times the natural log of n. And this is 1 over n goes to 0. Natural log of n goes to infinity. But we can easily turn this into a fraction. And we can see that we get natural log of n over n. And because we know that the limit as n approaches infinity of the numerator is equal to the limit as n approaches infinity of the denominator is equal to infinity, we know that L'Hopital can apply, and we will take the derivative of the top and the bottom and get 1 over n over 1, and that limit equals 0. The natural log of the value equals 0. That means that if the natural log of y equals 0, that means that y equals 1, because e raised to the 0 equals 1. Which means, back up here, that we've got 1 over 2. Ha-ha! All right, so 1 over 2 is in fact less than 1. Therefore, the series converges absolutely by the root test. Alrighty. Cool. So that leaves us with 2 more examples to go. I think we can fit these in one video. We'll see how it goes. Famous last words. Alright, let's change colors. I'm feeling saucy. Let's do purple. Limit as n approaches infinity of the nth root of, yikes, n factorial raised to the n is about the biggest thing I've ever heard of. And then n raised to the n squared is pretty ginormous too. But we're taking the nth root of everything, so we can simplify this down. Divide each of these exponents by n, we get n factorial in the numerator, and we get n squared in the denominator. Well, okay. Yeah, this goes to infinity, but come on. Factorials grow crazy fast. In that hierarchy of infinities, these things beat almost everything. So this is definitely infinity, which is definitely greater than 1. Therefore, the series diverges by the root tests. So it's pretty quick sometimes. That's nice. All right, last one, guys. Last one, number 10. Oh, we can probably do this one in our head, can't we? We'll do the limit as n approaches infinity, the nth root of the nth term, the exponent and the index cancel each other out, and we get a very simple 3n plus 4 over 2n. Again, just a horizontal asymptote at 3 over 2, which is greater than 1. Therefore, the series diverges by the root tests. Huzzah! Feel like I should zoom out so we can see all the tests, all of the examples of the root test. Too far. I guess we can't zoom in all out. Yeah, there we go. Yeah, a nice summary of the 3 examples of the root test.